Today is the day 3 of the program. We are starting the lecture 7 and the topic is on overview of DC-AC or AC-DC power converter topologies used in green hydrogen energy system. This will be provided by Professor Jahangir Hussain. Over to you, sir.
Welcome everyone. So yesterday we talked about DC to DC converter. So if you remember that DC to DC converter used in both cases like electrolyzer as well as fuel cell, right? But DC to AC or AC to DC, I mean not used in both cases. I mean unless you have got other renewable generators. Then so for fuel cell we produce DC output, right? Then I mean for utilization, if you have got AC load, then we need inverter, right? So that's DC to AC, that we call inverter, right? But for electrolyzer, what do we need? We need to supply DC voltage. So we need AC to DC converter, but we also call it rectifier. So here would be mostly a rectifier and inverter. So these are the content that I'm gonna talk about. So initially I will start with why actually we need AC DC or DC AC. I mean that's I already actually mentioned. And then when you're gonna select either rectifier or inverter, what actually you expect from them to be utilized either in electrolyzer or in fuel cell, right? And then we'll talk about few topology because I mean there are so many topology, but those are mostly already utilized. I'm going to show them, and then we'll show some comparison because you always need to know like pros and cons for every topology that's available. That will help you for your particular application, which one actually you can pick up. And then I'll also touch some converter driven stability. Although I mean we are talking about control, so before designing control also you need to know little bit about the stability and what actually makes the system unstable. Unless you know the exact reason why your system is unstable and who is making the system unstable, then I mean you won't be able to design control that gonna help I mean to make the system stable. So you also need to know have some knowledge about stability as well. I believe you might already have it, but we're gonna just touch it. I mean if I find, and hopefully I'll find some time. So I mean we talk about many times that that's converter actually plays a significant role in ensuring like efficient conversion, control, and also grid integration. And for like hydrogen, mainly for like electrolyzer, we need actually high power, high current devices. So although there are many inverter converter available, but here for our application we mostly need high power and high current. So this is also I mean already for you already clear, and I already mentioned that from fuel cell we convert DC to AC for connecting either with the grid, and even if you want to supply load, that is AC. But if you have DC, then probably, but again I mean even if it is DC, although we are not showing the middle stage DC to DC, but again I mean we need probably DC to AC. So in both cases we might have like here like DC to DC converter as well. And in electrolyzer, as I mentioned, like it needs DC, so you need to convert from AC to DC. So as I say, like to find out which one might be applicable for certain application, that depend on like the feature of the inverter, converter, or rectifier. So again, I think that's we already covered the function and need for rectifier. So I mean, if you supply from DC, I mean from photovoltaic system, you might not need rectifier because that's already DC, but then you already need like DC to DC converter. But if you want to, let's say, supply from wind farm or any other source which produces like AC, then definitely we need rectifier. An inverter, I already mentioned that if you, I mean, from fuel cell we produce DC, so we need inverter. But also, I mean, if you have any energy storage system in the devices, also I mean, you need inverter as well. So that's, I think we already have covered, no need to repeat. Now what actually you are expect, I mean, if you want to find out a rectifier like for powering electrolyzer. So as I said previously, that we need like a high power rating, because as you already know that electrolyzer could be like already like in the megawatt level, right? There are kilowatt as well, but it could be gigawatt level as well. So we need a rectifier that has got significant like power capacity, and if in most of the cases what we do, that we use like many of them in parallel to, I mean, increase their power capacity. So that probably when you have got like megawatt level, you might use like parallels module as well. And then for electrolyzer also we need very precise DC, right? Exactly, I mean, whatever voltage I mean mentioned, you need that. So that's why we need like a controlled DC current and also controlled DC voltage for optimal operation of the electrolyzer. So that's, we have to make sure that it's not only DC, but it's like controlled DC, both voltage as well as current. Another important requirement, that it has to have like very negligible ripple. I mean, if nothing, then definitely best. But as you know that most like we use like different converter, it does produce ripple. So that's why we use like filter to remove them, but it's still sometime we have ripple. So you have to make sure that for other application might be okay if you have slightly bit ripple, although I mean we don't want for any application, but for particularly for electrolyzer, we need to have, I mean, DC with negligible ripple. And what happens when you have very low voltage and low current, even sometime it produces more ripple. So that's also we have to make sure when we're gonna use it, either in experimental system or real cases. And also like the power factor, we have to, I mean, this is mainly for like the AC side. So power factor, I mean, we always expect close to unity, but you know that in most cases we don't have unity, but we always try more than 9495, just to minimize that it does not like draw reactive power from the system, right? So what happens, like even in your home, if it like draws reactive power, that means whatever appliances we have, if we have lower power factor, what will happen, right? So at then it's gonna be having reactive power. So that means but your load, mainly, whatever output you are getting from the active power. But as you know, that due to the nature of the electrical network, although we want like active power, but always there are some reactive power in the system. But we want like as close as to unity, because then you will have very less reactive power. So that's why we also want close to unity reactive power. And then the total harmonic distortion, that's also depend on the power quality. So we want very low total harmonic distortion as well. And in most of the like standard, for example, this is IEEE, and also there are IC standard as well. But most standard needs that your total harmonic distortion should be less than 5%, right? So any device you design or you want to commercialize sell, when they do the testing, they will make sure that it's less than 5%. If less than 5% is accepted, but even lower is always better. And then we definitely want that it will have wide input voltage and also the frequency tolerance. So in that case, when you have fluctuating power from like either renewable sources or from weak grids, still your rectifier can works. Although we mentioned that we want constant, but at the same time, if it is have that wide range, and if for some reason if exceed that certain value, still your rectifier would be able to your electrolyzer should be able to work with the input rectifier. And dynamic response, definitely we want that ability to quickly adjust the DC output based on the command from the plant, either to ramp up hydrogen production, because depending on your requirement, you can anytime ramp up hydrogen production or reduce the hydrogen production, right? So in that case, your rectifier should be able to meet that requirement. So if you give command, it will increase, or if you give command, it should be reducing, but that will be done by the controller. Okay, and yesterday you have learned many of the different controller, right? So you can apply anything based on your requirement. Like PI, normally industry widely used because it's easy to design and also implement. Although you need to change the parameters if your condition changes, but there are so many algorithms also you can utilize to find the exact parameter, and if you actually find the optimal parameter, sometimes PI works much better than those very complex linear and non-linear controller. So that's the reason. Still that's one of the most utilized controller in the industry. But having said that, some industry they are also utilizing sometimes that advanced MPC, model predictive, and in other adaptive control as well. Same for like inverter also. It would be quite similar requirement. I already mentioned that total harmonic distortion. Here also definitely we want less than 5, and then precise voltage frequency, that is also quite similar. But also in the AC side, you need another requirement for the synchronization. For DC, there is no problem with the synchronization because there is no frequency, right? But for AC also, you have to make sure that it has got the ability to accurately detect grid voltage, frequency, and phase angle, so that actually it can synchronize when it is connecting with the grid. So that's also another requirement. And mainly those of you like works with the microgrid, that's also like when microgrid go from like grid connected to island and vice versa, that microgrid also should be having the capability. So from islanded to grid connected, so that it can automatically synchronize with the grid as well. And I believe you know like what are the requirement for synchronization, like voltage, frequency, phase angle, everything has to be same. And also, I mean, mostly probably you know that every grid, like either Indian grid, Australian grid, all grid they have got some grid codes. So if you want to connect any new power plant with the grid, so here, for example, in Australia we have got Australian electricity market operator. So we have to do number of tests to show that it actually satisfies the Australian grid code requirement, and same thing would be in India as well. Like if you are a private or you are having like your own some power generator or a small power system, and if you want to connect, then you have to show that it compliance grid. And compliance grid again mainly the voltages, frequency, sometime n-1, n-2 requirement. Like if any of the device get disconnected, still it should be able to meet the grid requirement in terms of voltage, frequency, power quality. Anti-islanding protection, that's also like many of the devices that have got that protection there, so that it can detect the loss of the main grid and automatically disconnect it to protect like a utility worker or equipment. So for example, that you have like one electrolyzer, for example, connected with some part of the grid, and in some cases if it is disconnected from the main grid, that means it is like islanding. So that devices should have that sensing that grid is disconnected, and based on that the protection system can activate, like either to shut down or whatever, or working in other mode. But it has to have that capability for islanding detection and protection. Fall right through, I already mentioned previously that it should also have the ability to stay connected and supply at least, even not the rated amount of power, but at least partially when there is a disturbance in the grid. So for example, let's say you have got fuel cell, it produces I don't know, maybe let's say 50 watt, right, 50 kilowatt, and if there is a disturbance, then still it should have the capability to supply partially electrical power. So still we don't have that many fuel cell, but for wind turbine and even many of this photovoltaic system inverter, they also have that requirement that you cannot just completely disconnect it when there is a disturbance. So you should have that fall right through capability, and gives support function for inverter, that active reactive power control, sometime voltage, frequency as well. And also with this grid forming inverter, that also provide synthetic inertia to the system as well. And that's one of the topic, grid forming we're gonna talk about to the next session. Same like the other one also, it should be accommodating like a range of the DC voltage that might be coming from PV or from fuel cell. And then if you have like PV, the MPPT also should be connected with the PV to provide like maximum power output from the PV under any operating condition. Now so far, like for electrolyzer to convert from DC to AC, in the most of the existing like electrolyzer, it use like 12 pulse or 24 pulse rectifier. Now in China, I will show you the next example. They already have a big electrolyzer, and they are actually using those like 24 pulse, not 12 pulse, but the 24 pulse. But mostly like 12 or 24 pulse rectifier actually used for electrolyzer application. And the rectifier could be thyristor, IGBT, and also sometimes diode as well, right? and you know, like the difference between diode and diode is definitely uncontrolled, but if you have thyristor, it would be like a controlled rectifier, right? So we are not going for that basic principle of rectifier, because you already know from, converting from AC to DC. But what we have it here, you can see that here we have initially in the grid side a filter, then we have got like 12 pulse transformer, but if you have got 24, then also you need like 24 pulse transformer, and depending on the how many pulse, you will have the phase angle. Now here you have got two 6 pulse thyristor, which are connected in the two secondary side of this low frequency transformer. But again it's not that always you have to use low frequency transformer. So the existing one has got low frequency transformer, but as you know that people also working for other transformer, and Dr. Animesh yesterday mentioned that SST, that's like a transformer with power electronics that even has got better, not only stepping up or stepping down, but also it has different control capability as well. Now here you see that that silicon control rectifier, you have got this firing angle alpha. So by adjusting the firing angle, you can actually control the current, and depending on that, also what angle you are operating, depending on that, you're gonna get like in the output voltage and current. But when you have got very low amount of current, actually it produces more harmonics. So that's such that the low power operating condition, actually it produces more harmonic, because that time also have got reactive component as well. And as you know, harmonic, as you know that we have got like third harmonic, fifth, like and so on. So by using this Y delta configuration here, that actually when you have got that configuration, although you are not going in the transformer connection, but with that connection actually it can actually cancel or eliminate fifth and seventh order harmonics from the current. And then by using that transformer trap filter, it also actually eliminate 11th and 13th of the order of the line frequency that's are commonly used for power to hydrogen converter based on this 12 pulse thyristor rectifier. So from here, this pulse coming here, and from thyristor, then you are getting the DC, and then again this this capacitor again used to eliminate the ripple from the output voltage. And then again we are not showing DC to DC converter, but you might have DC to DC converter as well, and then we can supply to the electrolyzer to produce hydrogen. So we already talked about that it can suppress these harmonics, that improves overall power quality and reduces filter requirement, and this is well suited for large electrolyzer. Output voltage can be regulated by using the firing angle, because when you we are not developing the equation, but when you have that equation, you will see that in the output there is a relation with the alpha. So by changing that alpha, you can easily control that output voltage, and it's already like proven technology in the industrial environment. But here definitely one of the limitation is that this transformer actually very bulky. That if you have like megawatt level transformer, the conventional transformer, it's actually bulky and you might need big vehicle. I mean, even if you want to take it from somewhere, and this is not even cannot provide bidirectional. It has got slower response compared to active front end converter. That's probably going to talk about later. And power factor also goes lows when you have got lower output voltage and larger firing angle. So definitely, I mean, if you remember the sine wave, so when you have got like lower firing angle, so that means you get higher voltage, but higher firing angle you get lower voltages, because the relation like cosine of alpha. So that's like the first configuration. Now the next one. So here also, I mean, we have like 12 pulse transformer, but the difference here you can see here that here we have got like this DC to DC converter that we already talked like previously, that interleaved Bach is interleaved DC to DC converter. Now when this like when you have this like DC to DC converter, the main advantage is that you can have like high quality power output compared to the previous one, because it has got very good control capability that we already mentioned previously. So definitely the biggest advantage, the improved power quality, like in terms of lower distortion and also better power factor over the wider range of the power to gas converter. And it definitely, as you have got those filter and other things, so it can also eliminate those harmonics as well. So here, although it's going to be a little bit more expensive, but this one can provide better power quality. So definitely, I mean, low total harmonic distortion, no extra power switches in rectifier, voltage current regulation, improved power quality, and also it's scalable and modularity as well. So you can add more capacity, I mean, if you need in any point of the time. And when you have this, definitely it has got benefit for the electrolyzer operation in terms of lower stress, heating, increased reliability, reduced switching losses, and also it allows precise control, less filtering required, and better compliance with the grid code. And the last one here is again we have got additional device. I mean, if you compare with the previous, I mean the first one, that we are adding additional active shunt filter, because as we mentioned that at the low current we have got like higher harmonics as well as a total harmonic power quality issue. So here we can even reduce that by utilizing another shunt active power filter as well. So that's the difference, I mean, if you compare with the previous cases. So again, that's low total harmonic distortion with that shunt filter, and once we have got low harmonic distortion, that it's going to also reduce the reactive power losses, and definitely that's going to be grid friendly, and it will improve power factor. Definitely it will comply with the standard and grid codes. Now if you compare, there's like three different topology that we talked about. So here this one actually comparing the power factor for the electrolyzer. So, initially this is like at the beginning of the lifetime, and this one like more on the end of the electrolyzer lifetime. Now, which one we showing the best performance? That configuration that we mention here, that one of them has got shunt filter, other one we have got this multi-phase chopper with the diode rectifier. So, here if you see the dotted one, that is showing the best performance. So, the power factor is not unity, but it could be like 0.99, right. So, the second one which has got that DC to DC converter, that is also quite good. Although at the low current it has got slightly bit lower power factor, but then it's quite good. But if you see here, the initial one only thyristor rectifier, it has got very low power factor, mainly when you have got the low current, right. But you might ask like why it's showing better performance here, right. So, whatever power factor you can see here at the end, at the beginning of the electrolyzer installation, but we are getting higher when it is like more at the end of the electrolyzer lifetime, but it should be other way, right. Normally we get better performance in the beginning, right, but the reason actually here, because what happened, like that's the like when they actually goes at the end of the aging process, the increase in the electrolyzer resistance. So, when we use for a longer period of time, it actually increases the resistive value, right. So, when we have got higher resistance, what will happen? Power factor will be increased, right. So, that is the reason here, although other performance parameter might degrade, but the power factor actually get better due to increasing the resistance. So, that is the reason. So, here again I have given all the explanation that if you consider the power factor, which one is like best, which one is the middle, which one is giving poor performance, mainly when you have got the lower current, but definitely there is a difference in the price. So, depending on your requirement, you can pick up like which you gonna utilize, and even if it's not that, you cannot use like 12 pulse thyristor rectifier. So, when you have got like lower power factor, there are other option as well. You can still improve power factor, right, using, but the requirement is that you have to use additional device, right, and there are many like device available in the market to improve power factor, right. For example, like people use shunt capacitor, people can also use flex devices like static var compensator, which is called SVC, and also like other components called static synchronous compensator, which is called StatCom. But again you have to invest like to buy those devices, but the solution is available in the market even if you use the thyristor rectifier. So, but at the end that gonna also increase the overall cost. So, you have to find out that if I use 12 pulse thyristor rectifier plus SVC, what would be the cost compared with only I'm just using the third one for rectifier. What about the total harmonic distortion? So again, if you see that the one with the shunt power filter, that's giving the lower total harmonic distortion, in both cases, either in the beginning or end of the electrolyzer lifetime, compared to in both cases. So none of them within the 5%. So definitely you need, probably if you use this, you need additional filter to bring them back below 5%, but this one is already below 5% for total harmonic distortion. So that's, we already talked about that comparison. So again, this one even giving a better picture. So not only a power quality, but also efficiency, control, reliability, cost. So again, this would be slightly bit than higher cost than that. But some of them have, because this is more like established technology, so it might have very good reliability and also good efficiency as well. But in terms of power quality, this is poor. So again, as I say, which parameter is more important for you, based on that, you're gonna pick up which one is the best solution for a particular project. Now the next one is quite similar, but here it has got 24 pulse, and instead of using the normal low pass frequency, here they are using low tap changing transformer. So have you heard about this one? Probably you know about that, right? And why we use low tap changing transformer? To control voltage, right? So when voltage goes beyond the required boundary, the tap automatically changes, either to increase or decrease the voltage. So here also, if you use this one, it does have this additional function, and also using this one and then thyristor angle, you can also try to maintain the requirement for the power quality and power factor. So this one actually serve both purpose, not only the producing the phase shift, but also it has on low tap changing option as well, because sometime only a single device cannot meet the requirement. So multiple thyristor again might be connected in parallel. Now if you compare the overall efficiency, so only the thyristor rectifier, they are having efficiency almost in the more than 99%. But if you consider the losses in the transformer is also highly efficient, but then overall efficiency would be here around 97%. But as you know that for converter, inverter, now there are so many in the market which has got very, very high efficiency. So the overall efficiency is still here more than 97%. What else? This one also have good control over the electrolyzer current and power, so that can meet the requirement for the electrolyzer. And this sorry, the next one is not the thyristor, this one actually IGBT. So this is the IGBT rectifier, and then you have got IGBT like converter as well. So using this one again, I mean this one has got the better control capability compared to the previous one, as we discussed in the 12 pass cases as well. So this one efficiency, I mean compared to that one slightly less, because you have got like again DC to DC converter. So with that again efficiency is more than like 98%. But when you do the combined efficiency, it would be around 96-97%. This is the last one. Here we have got diode, like as we mentioned in previous cases, but here we are not having any like active power filter. But other than that, I mean we do have transformer and then rectifier and then converter, and then we are applying power to the devices. So this one also I mean have optimizers like the power quality, mainly providing like high power high current applications, because as we talk many times, this has got very precise control over voltage and power, this converter. So that's why it gonna produce I mean good control input voltage to the electrolyzer. Now this one actually, I mean as I say, in China they have already installed and they have experimental result as well. They published and they provided some cost comparison in their own currency. So you can see that definitely IGBT is would be slightly more than the thyristor, but all the comparison between these two rectifier is provided in terms of DC output power, rectification efficiency, AC output power, but both of them like 5 kilowatt. So it's same capacity, so that give you like a good comparison. So that's all about a rectifier. Now we're gonna go for inverter. There are so many inverter technology you will find in the market, and inverter used not only for fuel cell but other grid tied generator, battery energy storage system. But again the function is always converting from DC to AC. So it could be the DC from either fuel cell, DC from PV, or even DC from the battery. Some of them like single stage, some of them multi stage, some of them unidirectional, some of them multi-directional, even some of them have like multi-level. We have also like either current source or voltage source, which is more like grid following and grid forming. So there are so many technology available, and this is also, I mean there are established topology also used for the inverter as well. But here for the fuel cell application, definitely the requirement would be that first we're gonna be like boosting, and then we're gonna maybe converting from AC to, because fuel cell output voltage might not be that high, right? So before applying to the inverter, we might boost the voltage first, and then we convert from DC to AC. So in most of the cases we will have like a single device, which is the combination of a boost converter plus inverter, and there are already available in the market that the single device using like one shared like leg, it can does both like boosting and then I know it can invert from DC to AC. Now again, I mean also like whatever converter use, we expect some features from them as well. So mainly, I mean if you thinking about going for islanded application, we will think that it have like grid forming capability, but you know if it is connected with the grid, I mean we might not be needing that feature from the inverter. We also expect like the fast dynamic response if we want to provide ancillary service to the grid, providing voltage and frequency support. Definitely like all other devices, it should you know satisfy the standard in terms of the power quality, as I mentioned, less than 5%, and also it should provide voltage regulation at the point of common coupling. And when we are using the solar, I mean also it should be doing like the MPPT as well with the DC. Now here you can see one of the solution, I mean for using in the fuel cell. So if you see here, this is like that inverter, right? So just probably better would be, I mean instead of discussing this one, I will discuss using this one. So here, I mean if we not, because that one already combined, if we not combine, what will happen? I mean you see here up to this portion, this leg, this is like DC to DC converter, right? So this diode D1, MOSFET S5, and then this inductor LB, and this input and output capacitor. So this portion is nothing but like a boost DC to DC converter, and then the remaining portion, that is like a with the filter, this is like the inverter, right? So why we need that for fuel cell application? Because as I mentioned that fuel cell output might not be enough, just after inverter to match like whatever the requirement voltage in the AC side. So that's why always we use a boost with the inverter. Now here, I mean if you see like this branch, actually what will happen, I mean instead of using this one, so like this D1 and S5 actually can be actually substituted by just like by using like a another just like another MOSFET. So that's why like in this like one of them could be common for inverter as well as converter as well, and that's why like for particularly for hydrogen application, I mean this type of, I mean if it is single stage, this type of topology used for both boosting as well as, here you can see that we replace the previous one only using this common leg for like both converter as well as inverter. And definitely if we have that, that's common in terms of like providing control. We don't need like separate control for, I mean DC to DC and then inverter. So in terms of control, in terms of efficiency, and it's like one integrated power stage. So this gonna be like better solution if you use that inverter topology mainly for electrolyzer applications. And again, I mean it's gonna be taking quite a long time, and if you want to see like all the voltage current waveform, but as you know that for all those like switches we have to operate that, we need the pulse we can apply, but I mean nowadays I mean it's not that difficult I mean to get those pulses, but here the good thing is that still you can see the inductor waveform which does not have I mean current I mean low frequency current ripple. So that's in that sense actually provide I mean good output, but again I mean what will get output is not exactly sine wave, as you say, like you get like a square wave, but you know that when you use like 3-phase multi-stage, I mean probably you can still you will have some like harmonics, but you can get more close to the sine wave. So again in the market I mean people, as I say, like they are working multi-level inverter. We have also 3-phase, we have like an impedance source 3-phase. It's not like that. There are so many topology available in the market, but as I said that only requirement in this case that we whatever topology you're going to use it, it should be like a DC-DC, and then it produces pure sine wave. That would be the like the best solution. So and if you use that H bridge, then number of depending on the number of bridges, you're gonna have like I mean harmonic distortion. More is always better because it would be more like close to sine wave, as I mentioned. And for utility scale application, definitely I mean we'll be preferring like multi-phase H bridge that gonna give like better application for grid application. But if you have got like a small size, you don't care, then probably you can go for lower bridge that gonna reduce the price, but you have to compromise with the power quality. So I'm not showing like all the inverter because as I said this is quite established, and I mean you already understand the requirement. So I'm just take like few minutes, then I'm gonna finish and we will go for question answer. So again probably like before going like the converter stability, just like what are the different stability problem you might have when like all those DC, AC, DC and different converters that we mentioned that's connected with the power grid, because like in recent year that all the generator, all the storage, even like the different loads, all are connected like with inverter converter. So that's why I mean if you go like 5 years back, we have only this. I mean at the beginning, if you think about 10-20 years back, we have only problem like rotor angle stability, and rotor angle stability only involves the stability problem with the synchronous generator, right? And then because what happened like previously, most power grid they operated very conservatively. Conservatively means that if like let's say one transmission line having capability to transfer let's say 20 megawatt, then probably they were transmitting only 5 megawatt or 10 megawatt. So they are always operating like 50% of their maximum capability, because the reason that power company they don't want to take any blame, that if something happen, I mean at the end the system gonna be blackout, and there will be so many issues, not only from the people but from the government and so on. So that's why they are I mean very conservative. But what happened, I mean when we only utilizing 50% capacity, what problem we'll have? It gonna increase the power cost, right? Because as a consumer, whatever price we are paying the price not only for energy utilization, right? We are paying price for energy generation, like high voltage transmission, and then distribution. All the cost add up. when you are paying the electricity bill, right? So when the utility use like 50% capacity of any devices, so we are not, I mean, maximizing the whatever, you know, capacity available. So at the end, it contribute to give like higher prices, right? So that's why what happened in recent year, as the electrical demand have gone up significantly in all countries like, you know, India, Australia, everywhere, because it's not only residential demand, but also demand from like, you know, different industry, and all the other sector, they are also like, you know, electrified, like, you know, agriculture, health, education, and so on. So that actually increases the demand, and to meet the demand, I mean, it's not only enough that we have got building like new power plant. So the most challenging part to building the new transmission line, because it takes time, right? And also it's quite expensive. So nowadays what happened, they are trying to utilize, I mean, whatever maximum capability they have, and that actually increases the possibility of not only the angle stability, but also the voltage stability, frequency stability. And not only that, when you have got different power electronics component, they actually introduce two different new type of instability. One is called resonance stability, and another is converter driven stability. Now people who are working now, like, you know, mostly in the power electronics area, they look for always this either resonance stability and converter stability. But also, I mean, the voltage and frequency stability, that's also getting common, because as I said that there are so many induction motor in the system, and also like, you know, variable generation and the load demand have gone up significantly. Most of the equipment, they are operating close to their limit. So that contributed like now thinking like, you know, I mean, to develop robust control and, you know, other even like, you know, advanced level non-linear control, even just to make sure that we can ensure stability. And not only that, I mean, we also having like, you know, different monitoring, online monitoring, that also help us to see like how the system is operating. Now also when you're going to go for like, you know, stability and control, also you need to know like the devices that you are using, what like the time frame actually they are working. So as Dr. Animesh yesterday mentioned that when we design control, we have to think like the bandwidth we need, right? So the bandwidth at the time and frequency, you know, that the relation is just like the inverse, right? So here, so if you are more interested like inverter driven, you know, stability, and then you are dealing with millisecond. But if you just go for like the synchronous, like, you know, stator, that would be even like tens of millisecond. But if you go for the rotor angle dynamics, which is we called electromechanical, even that like, you know, in the like, you know, tens of like a second. But even if you go for like other thermodynamics, it's like a longer time frame. So what I'm trying to say that depending on your requirement, also, I mean, when you're dealing with the model, when you're dealing with the simulation, you have to use different types of model, different types of simulation. For example, if you are more interested to see power electronics dynamics, then you have to model in this time frame, right? And also you need to do simulation that's electromagnetic. So you have to do the simulation that is electromagnetic, not electromechanical. So the electromechanical only for rotor angle dynamics. That will, if you do like RMS simulation, that will never capture your power electronics dynamics in your simulation. Okay. So what I'm saying that, I mean, depending on your requirement, the control dynamics, you have to pick up the right model and you have to pick up the right software. If you, do your own coding, that's always fine, that you just write the mathematical model and then you do coding. But if you use the existing software, MATLAB, they can do both RMS and electromechanical. But if you use PSSC, that cannot do electromagnetic. PSCAD, it can do like electromagnetic. So be careful that, for example, if you are trying to show like inverter dynamics and you are doing some simulation which actually does not capture the dynamics of the system that you are using. Probably you already know like what is voltage stability. It's just to maintain the required voltage. But sometime if it goes like that is continuously increasing or continuously decreasing, that actually shows instability. But also when you work with the system, from your experience, you might know that this system has problem, voltage stability. If something changes, it can have voltage stability problem. From your experience, you will be able to find out just showing like low voltage profile, heavy reactive power flow if you do the load flow, or inadequate reactive power support, or if the system is heavily loaded. If the system goes unstable, that might be a voltage stability. Rotor angle, that just maintain the synchronous operation. There is a like again, you can ask like, for example, let's say if the system like here goes unstable. So at the end, whether it's voltage, whether it's frequency, its system is unstable, right? So in fact, actually, when the instability, there is no actually classification. Instable means instable. But the reason we classify, because we need to find out what actually causes the system unstable. Is it voltage which initially introduced the instability problem in the system, or it is angle, or it is frequency? So once you know, then you will be able to develop the solution. But at the end, if frequency become unstable, voltage will also become unstable, and vice versa. If voltage become unstable, then frequency will also become unstable. But the important thing that which one initiating the process first. So that's the reason we classify, we do so many different type of analysis just to understand what the basic stability problem is. So that's why we do all those classify that I have shown previously, just to our own understanding and develop the solution. But again, as I said, like from once you work in the power industry and also do research, from your experience, you might tell that probably that actually causes the system unstable. Even from power system like configuration, sometime you will be able to say. So if your system having like that generator which is connected with infinite bus or in a big power system, here your system will never have voltage instability problem, because so the generator has got capability to control voltage. Here also you have got number of generator. But if the configuration is like that you have generator and then you're supplying power which is quite far using a long transmission line, and if this sort of system have problem, you will see that this might be a voltage problem, because here there are no support for voltage. And then finally the frequency, as I said, in recent year, due to having like low inertia, as all the devices acting very fast, we are also having imbalance between generation and demand. So once generation and demand varies, you will have either frequency up or frequency down. That means frequency issues. So I need to stop. So again, I do have few slides, but you can read about that resonance instability. That's mainly happen due to that, subsynchronous, resonance, like, the resonance, right? XL equal to XC, right? So that resonance could be between like his compensation or electrical behavior of the generator, and sometimes we have like, the mechanical resonance as well between the mechanical torsional frequency and also the turbine generator shaft as well. So mainly here, when you have got offshore wind farm connected to the transmission grid, you might have that problem. And then for the converter again, so the way that we design the control, considering that bandwidth, but sometime if your converter, like, as you see that we shown previously that the frequency range and so on. So sometime your converter and and other devices have quite similar range, and then they interact each other. Then sometimes they also introduce, like, that converter driven instability. Normally converter do helps to improve stability, but sometimes due to that control negative interaction between each other, it might also introduce instability in the system. Anyway, thanks for your attention. I'll stop here. Thank you.
So we'll take quick 5 minutes question, then we'll start the next lecture. Any questions?
For the rotor angle stability, actually the fast transients have to be neglected when we design a converter.
The converter,
it doesn't accept only, it doesn't trace out only.
the converter driven instability, you that converter dynamics when you are modeling. Otherwise, you will not see like the that problem.
Yes, sir.
In
so
the
can you
system.
suggest any reference wherein the design of that converter, how do we model it for such study?
Well, there are actually number of reference available. I'll definitely email some paper to Dr. Animesh, and he can share. And actually, I'm giving all the slide
Yes, sir.
to him as well. But definitely, I will include
So
some
that
paper.
one paper what you shared, 2005 one paper.
Yeah, I'll share some other good paper as
Yes,
well.
sir. Yes, sir. Thank you.
What is the voltage instability difference between the entire grid and the microgrid? How does it differs from microgrid to the main
Can you
grid?
please repeat it?
Voltage instability difference.
Voltage.
Voltage instability at
Yeah.
microgrid and the main grid.
Yeah, like voltage instability, microgrid might have, but the microgrid, more challenge in the, frequency than voltage, but it could have like, voltage problem as well. But again, the voltage problem mainly happens when in the system you have got many inductive load in the system. Because that what happened, like when you have got inductive load, even like in your home, sometimes you see that you turn on the switch and suddenly your power disconnected, right?
Where it is more severe, sir, whether in microgrid or in the main grid?
What is the microgrid? Definitely in the microgrid. Because when you have got
Voltage
main grid,
instability is severe at the microgrid.
yes, in the main grid, there are so many, big generator and many voltage control devices as well. So definitely, in most of the cases, it will be controlled by the, big system. But when you have got the small system, definitely, the microgrid will have more problem than the, the main grid. But the thing that I was explaining, that when you have got more, inductive load, induction machine load in the system, that might causes the instability problem. Because what happens, like when motor starts, it, to energize the magnetic field, it takes more reactive current from the system, right? And when take more reactive current, that actually causes voltage in the system, and that introduce voltage. And again, also, those of who are doing the voltage stability also depends, like whether it is short term or long term. Short term, the phenomena that I was explaining, that's short term, but sometimes voltage instability can also happen long term voltage instability due to that OLTC and over excitation from over excitation in the generator as well, exciter.